Hello, good afternoon, and happy birthday to me. I love my birthday, so I just had to share that news, the announcement, and thank you for your wishes. Today I'm going to pick up where we left off. We're almost done covering all the material in the course, so we're in record time. We're going to have 1 week to review things. Actually, we're going to have 2 weeks to review things. I'd like to wrap it up this week, and then next week I can start answering questions in the final exams. All right, so tomorrow we're going to have a quiz. I'm going to prepare a quiz for inference up to, I mentioned up to the end, up to here. What we did, let me say, yeah, so up to there. So you're going to have a quiz on formulas 4 and 5, but those formulas are drawn from the formulas above, so you pretty much need to know everything on the formula sheet except for the last row. All right? And I hope you can ask me in advance if you have any questions today or tonight or tomorrow before the review, because I will also give a live stream tomorrow at 5. Where did we leave off? Well, we did all of these. We did all of these problems. This one was a set of questions about calculating confidence intervals. This was given the conditions for the predetermined confidence interval level and margin of error. You could calculate the sample size. And here we ran, we conducted a two-sided test for the situation. The hypothesis we wanted to test was regarding executives' blood pressure, and we tested to see if they were different than non-executives, and we just focused on male gender. So that brings us here, number 6. And I am going to erase just this part to avoid confusion. So I derived this yesterday. These details are the formula. I'm going to end up erasing the whole thing. I don't want to do that. Oh well. No, maybe I should put it back. So what we have to tackle now is inference for mu where sigma so inference on mu. So it's educated guessing on what is the true mean, the population mean, where we don't know it, and neither do we know the population variance and standard deviation. Okay, so this is a very realistic situation. We are dealing with a new kind of variable. We don't have prior information on it, and we want to gather a sample, and from the sample and some theory, we are able to create an estimate, and we can even specify how precise the estimate is. All right? The catch is, if we don't know sigma like we did here to create the new standard deviation, in other words, the standard error for the sample, for the mean, or the sample mean, the sampling distribution of the sample mean. If we don't know that, we can substitute it with the best alternative, which is the sample standard deviation instead of the population standard deviation. However, there's a catch. The catch is we can no longer use the Z distribution. We have to move to using the T distribution. The T distribution is dependent on the sample size. What happens is the larger the sample size, the more narrow the t-distribution becomes, and it begins to look more like the z-distribution. So we were using the t-table, which had the critical values and tail probabilities. We just use the bottom row of that, and we use the bottom row of that because t becomes z as n increases. Okay, so as n goes up, that looks weird. So as n increases, t becomes z. That looks like, even though n is going up, the sample size is going up, you have to look down the table because n is increasing as you go to the bottom of the table. So let's look at that table together and talk a little bit about it. Then we're going to use the table, okay, to calculate first confidence intervals and then do some hypothesis testing. And I'll mention why it is that there is no way to do sample size estimation when a sigma is not known. Okay, just before we continue, I want to say one more time, just to recap what we've done for this course. We learned a lot of things. And that brought us to applying it. And we applied it with these three statements. We were able to derive concluding statements about sampling distributions. This is about the sampling distribution of the sample count. Number 2 is about the sampling distribution of the sample proportion. And number 3 is about the sampling distribution of the sample mean. And they're all used to do inference. So everything we did was to get us to the point where we were doing inference, educated guessing about what the population mean could be. Now, sorry, I'm going up and down. So to do any of these 1, 2, and 3, I assume I know the parameters. I know n and p, which are the parameters for the binomial here. And number 2, I know n and p, which are the parameters for the binomial. And then it turns out that I can convert this variable into a normal distribution. So then I also know the mean and standard deviation of that. So I know the parameters. For 3, I know the parameters to be able to talk about the sampling distribution of the sample mean. The parameters I know are mu and sigma. So you see, I know from 1 to 3, I know the parameters. There's no inference in 1, 2, and 3. I know the parameters, and I use them to make predictions of what to expect in a sample result. For 4, 5, and 6, I take the parameters away. So I take the parameters away, but we still use the structure we built above as our foundation to deriving the best estimates of those actual parameters. Okay? So that's how this works. All right, so let's see. Let's look at the table. Let's look at the t-table and know it better. Here's the t-distribution. Oh, you want to know how old I am? I should give you a math equation. There you go. I'm very old. But it's okay. I'm going to live to 101 to make up for it. All right, so let's see. We have, this is the t-distribution, and I mentioned to you before, even though we just used the last row, I mentioned to you that they're relatively flat distributions with 0 in the middle. I don't know if I mentioned that, but I'm telling you now. Oops. So 0 is in the middle. Okay. I can't see. Let me make this bigger. And as the sample size goes up, the t-distribution begins to look more and more, it's more tight and more like the z-distribution. The tails are the main thing here. You have more outliers, okay, in this distribution. That's basically what's happening. You have more chance for strange values. That's what it adds up to. So let's see, how do we do this? Whereas the Z distribution, the standard normal distribution, has the probabilities, the percentiles inside the table. Here, I have the probabilities on the margin at the top. And these are not left side probabilities this graph shows you. These are tail probabilities. Okay, so it's the inverse. It's inverted. The table's inverted. The image is inverted to what you do with the Z table, but it's effective. This is the standard table. Now you can get these results out of Excel if you prefer to use Excel and get more precision. Some calculators can calculate these results. Just make sure you know what you're getting. And we'll talk about some computer output, how you can read these results from the computer output. So let's see. What I have here, let's say I have, well actually I have some exercises. Let's do the exercises together. I'm gonna ask you to take that page. Hopefully you've printed the notes, because that's the best way to manage these notes. There's so many pages. Have the tables beside you, the formula sheet beside you, and let's work on interpreting the table. I have some problems here for the table on page 37. I describe and make some statements about the table here. So let's see, how would we solve using the table? Let me give you a couple minutes just to stare at the table and try and make sense of this. Maybe you know how to use it. I'm assuming you don't. So let me give you a minute just to look at this and orient yourself, and then I'll see if you can try and answer it, and then I'll spell it out for you. Okay? You appreciate it more that way. So I'll give you 2 minutes. All right, I'm back. Let me erase that. Okay, what you're supposed to do is identify first the sample size, and then what we really want is to work with the degrees of freedom. Remember about degrees of freedom. We lose 1 degree of freedom because of using an estimate in our estimator. So I won't go too much detail with that, but this is what we need to apply to the table. So n of 20 means degrees of freedom of 19. So that means we have to go on the 19th row, row 19. And what we're going to do is consider I want to know so I know 0 is here, so I'm going to just say I don't know all the details about inflection points and the shape exactly of the t distribution, but I draw it similar to the z distribution, and I know that the positives are on the right of the 0, the center, so I'm going to put 1.5 here, and I want to find out the tail probability of 1.5 being higher than that. So this is 1.5, similar to the z, we interpret that as 1.5 standard deviations above the mean. Okay? And I want to know what that probability is. So what do? I need to use the 19th row. So going back to look at that, maybe you guys can tell me, well, no, I'll have to do it because I'm going to be jumping, but I'll go back to page 39 when I'm done. So I go to row 19, which is this one here. Let's see if I can highlight. This is a highlighter, I think. It's not very fancy colors. Okay, so this is 19 here. And what is, oh, you can't see that. So this is 19 here. And according to the drawing above, this is providing you the threshold, the critical value, okay, associated with, with the probability at the top. So the first one, I'll just make it smaller. So the first one is 25%. So on T19, 25% is to the right of 1.688. And 20% is to the right of 0.861. So it's basically getting smaller. As the numbers go higher, right, I'm moving. As the numbers get higher, I'm moving more this way. So the numbers are getting higher, it's getting bigger away from 0. This is like a number line from negative to positive with 0 in the middle. As this is getting bigger, then that means that the tail probability gets smaller. Okay, so it's getting more in the area of the region of the outliers. So the value we got was 1. The one I want to know about is 1.15. So what I have to do is find it here, and then the closest is between these two, right? So then I go up here to see, I don't have the exact value. If you put this in Excel, you can get the exact value, but here you're just going to get between 5 and 10%. So let me draw that for you. So that's 1.328 and 1.729. So 1.328 is here, let's say. And I know it's not exactly there to scale, but 0.729, just give you an idea. So this area red is 5%, and this is supposed to be 10%. And so our 1.5 is somewhere between those two. Okay, that's how I read the table. And there's all kinds of questions I can ask you, but this is the way we'll be using the table for the tail probabilities. Right. How's that? Let's do some more. Why don't you try the next few? I'll give you 5 minutes. So try the next few and see. So actually, let me write the final answer. So the final answer is the probability of the t distribution being greater than 1.5 is between 5% and 10%. And I believe I have the answers on the next page. So don't look at the answers on the next page. I'll just flash them for you to see. See what I wrote? I wrote it sandwiched between 5% and 10%. So that's the answer. So keep going. Try the next problems without looking at the answers. We'll do that together. I'll give you 5 minutes to just do them all. Okay, do them all. And we'll regroup. So 5 minutes to try. Cover up the answers. Okay, how did it go? Any of them give you particular trouble? Let's see, I'm going to do a few of them. You can let me know. What if I want to go left, not the other way? So I'm not interested in the tail. Let's say I'm interested in the complement. How will I solve that? Well, let's just use the idea of symmetry, not symmetry, but the idea of complement. Take it from what we learned before. And what I want is now the other side. I want this over here. So between, I don't have to redraw it, do I? If the answer here is between, %5 and 10%, the answer in number 2 is the complement. What would be the complement? It's 1 minus. So I want to go in numerical order from smaller to bigger, right? So I would say, well, this one, the complement of this is 90 and the complement of this is 95. So I need to flip that and say between 90% and 95%. All right? And I got that answer because this also was for an n of 20, just like this one. So you always check that, which I didn't at the beginning, but I knew where I was headed. It always verifies. So it's the same row, so I just take the complement. Let's try the next one. Okay, draw a picture. Just so that it's a systematic way of doing this, so you don't get confused. So draw a picture. I draw T6, right? Because I want the degrees of freedom, not just n. I need n minus 1. So degrees of freedom is 6. And I want to know the left side of negative 1.44. Okay, so the 0 is in the middle. So the negatives would be here. And I want this for negative 1.440. I made this easy, but because I made it one of the numbers in the table to give you some hope of knowing what to do. Try and erase this a little bit. Didn't want to do that. Okay, well, I want this area here. The table gives me tails on the right side, so I can use the property of symmetry to depict this and say, well, what if I just get this one and then it has to be the same area, right? These have to be the same because of the symmetry. So now we're really using the symmetry of the distribution. Let's do that, and the answer I get here will translate off of the T6 table. It will translate to be the same answer for that one. So if we go to T6, the 6th row, on T6, we look for that number. That's how we do this. We look, and here it is. I have it exactly there. Now, in the first question, it wasn't there exactly, but I made it, I took a little bit of the trouble away from this problem. Notice they're all positives, right? So these are only for the positives, but you can use them for the negatives as well, as long as you know what you're doing. So this tells me that the upper tail probability is 10% for 1.44. So that means that means that this is 10%, which means that this is 10%. So the answer is 10%. Okay, so this is easier to use in the z-table, I think, and not just the nature of the questions I'm answering with it. Let's keep going. The next one, let me draw it, always draw it. I'm going to draw it with T20, not to be confused, to anchor myself. I'm going to use the 20th row, and I'm going to again ask you about a negative value just so you understand how to get negative values off of the table. Negative 2.086. Negative 2.086, and I want to go this way. So I go to my table and I look on the 20th row, right? Because it was 21. And I look for negative negative is not going to be here, but I find the positive version. So what do I do with the positive version? The positive version corresponds to 2.5%. So that corresponds to 2.5%. So what is 2.5%? Well, it's certainly not that way, right? It's the other way. 2.5% is the area over here. How do I know that? Because the table only gives me the right tail. So I would be getting 2.086 up here for the T20 table, and this gives me 2.5%. And so then the tail here is 2.5%. So what does that mean? And again, I'm making this precise just to take a layer of complexity out of this. It doesn't have to be precisely the number. It could be anywhere between, and we have to use the between approach. Now we're doing that because there's not a lot of values on this table. There's only 12 values for each degrees of freedom. So each curve that you make for T only has 12 values on it to work with. Okay, so you've got to make the most of it. So 2.5 on this side means 97.5 on the other side. So the answer to this question is the probability is 97.5. All right. What about I'll circle the right answers. If somebody is skipping through this gets confused. The right answer was this one. Okay, there's two more now. Now I call these type 2 problems, remember, because these are the backward type problem. What if I'm not interested in the probability? What if I tell you what the tail probability is and you have to give me the t-score, the t-stat, or the t-critical value? Those all mean the same thing. Oh, sorry. So what I'm saying is, let's draw it. Draw it. Always draw it. This says the probability that you see a t statistic, a critical value, greater than t. So the curve, in other words, the curve greater than t, so the tail probability, is very small. So I'll just draw that. The tail probability is very small. Let's say it's here. This is just a sketch, but you get the point. It's very small. This is here. And it is 0.005. The question is, what is the t? What is t? What's the t critical value for that? So how would I figure that out? Well, I have to do things backwards, right? Rather than looking inside the table and going up, I'm going to start on top at the probabilities and then go down. So let's see. Which road should I go down to though? I need to go down to T16. Okay, can you read that? T16, right? Degrees of freedom. So I'm going to do that. And go down to T16. So among these options here, look for 0.005. Oh, now I can't remember if it was 0.0005. I think it was, right? Anyway, so it's either 2.921 if it was 0.005, or 4.015 if it was 0.0005, and I can't remember which one it was. So let's see. I'll just look for the answer in my options. Right, it was 0.005. So it is t of 2.921. The answer is that the t-stat is 2. What did I just do? T.2.921. Right, so 2, almost 3 standard deviations from the mean of 0 is going to have a tail probability of 0.005 or 0.5%. And the last one for T9, let's draw it. Oh, that's a terrible drawing. This is T9, I know that because n is given as 10. And for T9, I want to know what's the t critical value, t-stat, not t-stat, but t critical value, right? Because I'm reading off the table. It's not a calculated value, it's actually like a t-score. It's not calculated from a sample. So now for T9, I want to know what's the t that gives me on the left side a small value. So that's going to be over here. I'm going to draw it. So that's 0.005. No, what am I doing? Sorry. Oh, editing. I want to put t equals, I don't know what it is, but it's got to be negative. Sorry, let me do that again so it's not so messy. Let me make this bigger. So I'm going to say t equals question mark, and this is 0.005, and don't I know that answer? I do know that answer because, oh, actually no, wait, I don't get caught up. The n was 9 here. What was the n over here? Oh no, that was a different n, so that's not the answer, but we do know how to do this. We're going to solve it for the positive version and then use the negative. So if you change the direction and the sign using the symmetry, the results for the left tail will be the same as the right tail. So let's draw that up here. For the right tail of T9, I want to know if this is 0.005, and this T, question is, what's the T here? Go to the table, from the top, find 0.5% and go all the way down to 9. Try to have amnesia about the one before, don't get confused. But go down to the 9th row and pick up what the critical value is, what the t-score is. So we're going to the 9th of 0.005, and it's 3.250. So 3.250 probably a better way to present this, but this is the best I can do for now. So what I found out was that T must be 3.250 in the table. So that means, to answer the question on the left tail, on the left side, the answer is negative 3.250. So that's how you use the table. Okay, I'm going to do it on the other end, not to be confused. Okay, so that's what the T would be, and that's your answer. So this is your answer here. The problem above. This was my answer. Okay, so that's T. So how do you guys do? Not bad? That's how you use the T-table and the way that we want to use it. Those are the most important ways to be able to use it. And notice the backwards problem is very easy. With the T, you should feel that it's easier than using the Z standard normal table. So now what do we do with this? Now we solve for confidence intervals. We conduct hypothesis testing. So we have 10 minutes. So all of these problems have answers, right? All these exercises have answers to them. I think I'm just going to ask you to work. Well, I know you're going to want to study for the other stuff right now, but maybe, let me see, I don't know how much time we have to actually. That's a really good exercise. These are all good exercises. And we're pretty much done the course because that's the last thing. It's just a matter of doing exercises and exercises. So, okay, what I'm going to do is I'm going to explain from the formula sheet, because this is just a matter of application. You know how to get all the elements. Just remember, so the first question you have to identify, the first question you have to answer is this a problem about means or proportions? That will tell you whether to refer to row 4 or 5 or 6. Okay, so if it's proportion, you go here. If it's about the average, you go here. So if it's about polling or percentage of damaged or defective bulbs, or about the proportion of people who dislike or have preference for something, that's all proportion. Proportion of cars that are left in a parking lot, those are kind of questions. If it's a question about weights and heights and sales, then it's about means, and that's where you go here. You go here, and whether it's regarding, in the case of means, whether you've been given the population standard deviation or not. Okay, so The second question is really a matter of distinguishing between your sample results and your population results. So name everything. In your problem, name everything. 5, the results of 5 are preferred to the results of 6. So in any case, dig for the true population standard deviation to solve a problem. 6 is the second best. Okay? If you don't have it, you can substitute with S and substitute T in. Most of our, in reality, we mostly use the T distribution. Okay? In reality, you don't have the population standard deviation to work with. You don't have a prior study to draw from that you can assume you know the population standard deviation. So this is the most realistic abstraction of all of the course. Okay? So we can solve for confidence intervals. We can conduct hypothesis testing with a sample to test certain hypotheses. Is it true that the blood pressure of a certain group varies from the status quo? That was the example we did. Is it true that the salaries of CEOs increased? We can answer questions like that. But we cannot estimate the sample size this way that we did here for these other exercises. We can't isolate for n. You can estimate the sample size, but it's not done this way. It would be done with computer software. Okay, you would make or you could estimate it making an Excel table to estimate what n should be to balance this equation. Now, why is that? Why does that present a problem for us? So this is my question to you. My question to you is, why is it not the case that n equals z star sample standard deviation over m squared? And my question is, why can't we do this? Okay, I'm going to give you a few minutes to think about it. No, we have no time to think about it. Okay, I'm going to talk about that tomorrow, okay? I want you to think about it. It's actually in the notes if you want to read about it, but think about it. I'm going to go have my special birthday meal, and you guys are going to let me know if you have any questions, anything I can help you with in the first hour tomorrow before you actually write the quiz. I will also post makeup quizzes for you, okay? For the binomial, so what probability, binomial, and SDS. So you'll have those to do, and I'll leave them up till 10 o'clock. So again, work independently. You guys can study together, but not, on the test. Please try and work independently. Build your confidence. I want you to be confident about this material when you finish this course, and not that it's just a blur in your past that you did statistics for the first, second, third time. Okay, I really want you to take this information away with you. And then there's always the videos. I'll just leave the videos up if any of you ever care to come back. So have a good night, and we'll talk to you tomorrow. Bye.